Namaskaram. In this session, we will discuss Rank-Nullity Theorem and its properties. The solution of last homework. Okay, consider the theorem. Let T be a linear transformation from an n-dimensional vector space V to W. That means here the dimension of V is n. Okay, let V1, V2, etc. Vk be a basis for the kernel of T. We know what is a kernel of a linear transformation. If this basis is extended to a basis v1, v2, vk up to vk, this same set, right, or basis for a kernel, then we introduce new vectors, that is vk plus 1 etc. up to vn for v. That means this new set is a basis for v. Okay, we extend this basis such a way that the new set is basis for v. Then next we consider the collection of images of these new vectors. Okay, n minus k vectors. This collection of t of vk plus 1, t of vk plus 2, etc. t of vn is a basis for image of t. Clear? How many elements are there? This is n minus k, right? Here it is k. Total n elements. There is a basis for v. Okay, this means V and W are two vector spaces, and also we assume that dimension of V equal to n, right? There is no restriction for dimension of W. Then V1, V2, etc. Vk, it form a basis for kernel of the transformation. We know that kernel of the transformation is always a subspace of V, so it has a basis, right? Next, we have to extend this vector by adding new vectors Vk plus 1, etc. up to Vn. Okay. Then you think about the new collection. So new collection contains this basis together with the new n minus k vectors vk plus 1, vk plus 2, etc. vn. And what is the property of this new set? The new set is a basis for v. Okay, so this is called the extended basis. You can extend this set such a way that the new collection is a basis for v. Then this result says that next you consider the images of these new vectors, that is t of vk plus 1 etc. up to t of vn. Okay, how many? It contains n minus k vectors. Then this result says that this new set is a basis for image of t. Okay, so you can easily find a basis for image of t. Once we have the basis, then you can generate the image by taking the linear combination or taking the span. Okay. Next definition: the dimension of kernel is called nullity of the transformation and denoted by nu of t. This is called nu. The dimension of image of t is called rank of the transformation, rank of t, denoted by r of t. Okay. So in this result, what is our nullity of the transformation? Nullity is the dimension of the kernel. Here we assume that the dimension of the basis, this is a basis for the kernel. That means in this result, nullity is k. Clear? Nullity is k. And what about the rank of the transformation? It is nothing. It is the dimension of image of t. From this theorem, it is clear that this is a basis for image. So what is our rank? Rank is n minus k. So in this result, our nullity is k and rank is n minus k. So what about nullity of the transformation plus rank of the transformation? This is k. This is always n minus k. So this sum is n. This theorem is called Rank-Nullity Theorem. Clear? This is our Rank-Nullity Theorem. Rank of t plus nullity of t is always equal to n. What is n? N is the dimension of v, right? We assume that v is a n-dimensional vector space. Here we assume that v is a n-dimensional vector space. So this n is dimension of v. So this result is called Rank-Nullity Theorem. Okay, consider a problem. Find a basis for kernel and image of t. Okay, and what is our method? We can use this theorem. So first we have to find a basis for kernel, then we extend that basis such a way that new set is a basis for V. Then you simply take the images of new vectors that form the basis for image of T. That is a procedure. So our first step is finding a basis for kernel. Okay, we know that what is kernel of a transformation? Set of all x such that set of all vectors such that t of x is equal to 0. Okay, here t from R4 to R3. So t of x means this vector a plus b, b plus c plus d, a minus c minus d. So t of x equal to 0 means this is equal to 0. Okay, so we have to solve a system. Okay, here 0 means what? 0 is a 0 vector in R3, so that is 0 0 0. And what is t of x? Here t of x is, this is the image, a plus b, b plus c plus d, and a minus c minus d. So you can compare the similar terms. So a plus b equal to 0, this equal to 0, and this equal to 0. So we have to solve the system. Okay, how to solve? Better you use Gauss elimination method. So this is the matrix corresponding to the system 1 1 0 0 0 1 1 1. Right, here b is 0, b, the coefficient of b is 0, so 1 0 minus 1 1. Next we have to convert this in echelon form using row reduction. So first we have to make this one is 0. So R3 goes to R3 minus R1. Okay, so the matrix become, this is 0 and 0 minus 1 minus 1. These two are remains minus 1, minus 1 0 minus 1 0. Okay, so next you have to make this term equal 0 using this one. That means R3 goes to R3 plus R2. Okay, so this become 0 0 0. Okay, so this is the final form of the matrix. So what is the rank of the system? What is the rank of the system? Yes, it contains only 2 non-zero rows, so its rank is 2. And what about number of variables? Yes, here it contains a, b, c, d, 4 unknowns. Okay, so number of variables is 4. So how many arbitrary? So arbitrary variables is equal to n minus r, that's equal to 4 minus 2, that's equal to 2. We can make 2 of them are arbitrary. Okay, so I'm going to choose c and d are arbitrary. Okay, so next we have to solve everything in terms of c and d. Okay, we choose c and d are arbitrary. So the system corresponding to the final form is a plus b equal to 0, and this is b plus c plus d equal to 0. Okay, only 2 equations. And this means what? This means here one relation is dependent, that's why that becomes 0. Okay, anyway here we assume that c and d are arbitrary. So what is b? So b equal to minus c minus d, and from this equation a equal to minus b. So what is a? Minus of b. Minus of b means c plus d. Now everything in terms of c and d. We assume that c and d are arbitrary and a is c plus d and b equal to minus c plus d. Now we are ready to write our kernel. Our c and d are arbitrary, and what is a? A is c plus d and b is minus c minus d. Set of all vectors of this form c, d, c plus d, minus c minus d, where c comma d are any real number. They are arbitrary numbers. We assume that c and d are arbitrary. Okay, they can take any real value. Set of all possible these type of vectors is our kernel of the transformation. Okay, so now kernel is ready. Next we have to find a basis for the kernel. It is possible to write our kernel as a linear combination of 2 vectors. That is possible. Can you identify that 2 vectors? Yes, we can write kernel of t as c times 1 minus 1 1 0 plus 1 minus 1 1 0 plus d times 1 minus 1 0 1, where c and d are any real number. Okay, now it is clear what is kernel. This is nothing, this is span, set of whole linear combination of these 2 vectors. Let it be, this is our v1 and v2. Okay, let it be v1 and v2. So kernel of t is a span of these 2 vectors. Clear? So we can write like this, span of v1 v2. Then actually our aim is to find a basis for kernel. Now it is clear that we can span kernel of t using these 2 vectors, and we know that these 2 vectors forms a basis for kernel only when it spans and linearly independent. The span part is over. Next we have to check whether they are independent or not, linearly independent or not. What about these two vectors? They are independent or not? Yes, they are linearly independent. Why? Because it contains only two vectors and one of them is not a multiple of other. One of them is not a scalar multiple of other. So it is clear that this set v1 v2, this set is linearly independent. So what is our conclusion? The set, so this set is linearly independent and spans kernel of T. So that's why this set is a basis for kernel of T. So now we have one basis for kernel of T. So first part is over. Next we have to extend this set such a way that the new set is a basis for R4. Then take the image of the new elements that gives the basis for image. That's the procedure. So next we have to extend. Okay, so this is our v1 and v2. So this is our R4 and we know that dimension of R4 is 4. So a basis of R4 contains 4 elements. Already we have two linearly independent vectors v1 and v2. So our aim is to find a v3 and v4 such that the new set is a basis. This new set B is a basis for R4. So we have to add two more vectors. What are the two suitable vectors? What are simple two suitable vectors? There are so many extensions. This extension is not unique. So which one is simple? I think the better you extend this basis from the elements from our standard basis. Okay, already this vector contains a term like 1 0 and here 0 1. So I'm going to extend this one using the two elements from standard basis, that is 1 0 0 and 0 1 0 0. There are so many extensions. This is a one particular extension. I think better you extend always from the elements from standard base. That is easy. Okay. Anyway, now we have a set containing 4 elements. Next, we have to check whether this set is linearly independent or not. If it is linearly independent, then guarantee it spans R4 because we have a result. Okay. So our only job, only task is to verify this B is linearly independent or not, because it contains only 4 elements. Okay. Then how to verify this is linearly independent? We consider C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 equal to 0, and this implies all the CIs are 0, then it is linearly independent. Okay. So how to check? So you consider C1 into this one plus C2 into this one plus C3 into this plus C4 into this one equal to 0 0 0. So now you have 4 equations. What are the equations? Okay, these are the 4 equations. C1 plus C2 plus C3 equal to 0. From the second one, minus C1 minus C2 plus C4 equal to 0. From this one, C3 equal to 0. Sorry, C1 equal to 0. And this one, C2 equal to 0. Correct. These are the 4 equations. Already C1 and C2 are 0. If you substitute C1 equal to C2 equal to 0 in this equation implies what? If suppose C1 and C2 are 0, then what is C4? C4 equal to 0. Then again here C1 and C2 0. So this implies C3 equal to 0. So what is our conclusion? Everything equal to 0. C1 equal to 0, C2 equal to 0, C3 0, C4 0. So this implies C1 equal to C2 equal to C3 equal to C4 equal to 0. So what is our conclusion? This set is linearly independent. Then we have a result. Since the dimension of R4 is 4 and this is a 4 element linearly independent set, it spans R4. That means this is a basis for R4. Okay, so these two vectors v1 and v2 are the basis for the kernel. We extend this set by adding two new vectors v3 and v4. That gives a basis for R4. Then now you can easily find the basis for image of T. Suppose this is image of T. Then how to find the base of image of T? You simply take the images of new elements. That means T of V3 and T of V4. This new set forms a basis. So what is T of V3 and T of V4? Yes. So T of V3, that is T of 1 0 0 0. That's equal to, from this definition of T, it is 1 0 1. And that is this element 1 0 1. And T of V4, that is T of 0 1 0 0. our image of the second element, that is from this definition 110, that is our second element. And above theorem, previous theorem says that the collection of these two vectors form a basis for image of T. Okay, so what is the base of image of T? Yes, so this collection of these two vectors 101 and 110, this collection form a basis for image of T. So you can easily find image. You simply take the span. So what is image of T? Suppose the question is this, we have to find the image of T. Then you simply find the basis, then you simply take the span. So what is image of T? Yes, kernel and image. Okay, so you can easily find the image. Image of T is the span of basis elements. So C1 into this one plus C2 into this one. That is nothing, C1 plus C2, and second one is C2. Third one is C1, where C1 and C2 are real numbers. So the whole vectors of this form is the image of this transformation. Okay. Okay, this is your homework. Thank you.